Welcome back. So we've talked about the theory of plate tectonics, how it came to be, evidence and proof, why it occurs, mantle convection, the different type of boundaries and geology that relates to those. Now let's focus on how all of that plays a part in Arizona. So how did plate tectonics help to shape Arizona? But before we do, let me give you the super secret code. Here it is, right here. Now, sometimes I say it, like last unit. Sometimes I'll show you. Sometimes it's broken up over a number of videos. Sometimes if I show it, I won't even say anything. I'll be like, oh, plate tectonics in Arizona and blah, 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 blah. And I'll hold it up. Maybe I might make myself bigger or something like this. You just never know, all right? So again, these aren't meant to trick you. I'm not trying to, be mean and, make sure you watch every little last detail. If you're watching these videos, you're watching and listening, you'll catch these things and you'll do just fine. Again, the reason we do this is that you deserve to be with people in a group that put in the same effort that you have and at least been exposed to the same material that you have. Not that you all understand it perfectly, but at least you can guarantee that when you're working in lab, the people there have put in the work to watch the lectures. They've done the assignment. That's why they're there. So you deserve to work with someone, again, who's put in that same effort. So that's why we do these codes. All right. So again, sometimes I say it, sometimes I show it like I did here. Sometimes I break it up over a series of videos. Sometimes I'll show or tell you the code, and then at another video, I'll tell you to do something to it mathematically, like, oh, add this or divide by this, or whatever it may be. Okay. So as long as you're watching and listening and pay attention, you're going to come across these just fine. Fair enough? So that's the code for this week. Let's go ahead and talk about how plate tectonics has shaped Arizona. So I don't know if you've traveled around the state much, but if you looked at what Phoenix looks like versus what Flagstaff looks like, it's pretty different. And that's still different than what Prescott looks like. They're all different because these cities look different because they're in areas that were formed differently, geologically speaking. So there's really three geologic Arizonas. So if you think about what's happening down in kind of Phoenix is right here, so the Phoenix area, Tucson, Yuma, even up into Kingman, like all of these areas look pretty much the same, kind of flat, barren deserts with kind of mountain ranges jumping out of nowhere. Hot, flat, barren deserts, everything jumping out of nowhere. Flagstaff, kind of different. Higher elevation, obviously. It's also flat, but not desert-like what we see down here in the valley. But there are large mountain ranges, a lot of those being volcanic. The surrounding area mostly flat up here, but higher elevation. And then in between the two, we kind of have a weird zone. This is where Prescott and Show Low, Jerome, places like that, Sedona even for the most part. Those places kind of look different still. The reason? Because all of these kind of have different geologic formations that help to have crafted them. So there are three different geologic provinces of Arizona. One would be the Basin and Range province. That's where Phoenix, Avondale, Tucson, Kingman, Yuma, that's where all of these locations are. Colorado Plateau, places like Flagstaff. Transition zones is where you get Prescott, Show Low, things like that. So again, the Basin and Range province, we'll talk about a little bit more here momentarily. The Colorado Plateau, a lot of what you see up there is either volcanism or tied to sedimentation, deposit of sedimentary material. And then in the transition zones, kind of the in-between what's occurred down here in the Basin and Range province versus what happened in the Colorado Plateau. So most of the terrain in the Basin and Range province, Phoenix, Tucson, etc., that's due to plate tectonics, where, again, most of the terrain up in the Colorado Plateau is due to volcanism and sedimentation. So since this unit's mostly about plate tectonics, let's focus on the Basin and Range, because that's where we are, or at least most of us are. It's where EMCC is located in what we know as the Basin and Range province. So how did it get to be? Why does Phoenix and Tucson look the same? Even into Las Vegas, why does that terrain look the same? As you drive to California, up until a certain point, why does all that terrain look the same? What's going on there? Well, all of that is tied to plate tectonics. So it started way back initially when there was movement along the San Andreas Fault. Once the movement along the San Andreas Fault occurred, this kind of side-by-side motion, this transform boundary motion, Once that occurred, it caused Arizona and some of the other western states to look the way it does. So it was all started there. And the Basin and Range province extends through Arizona, up through California, almost all of Nevada, even up into Oregon and Idaho, over into New Mexico, down into Mexico itself, into Utah. So all these places look very similar terrain-wise because they were all formed via the same process. So how did that work? So again, once movement along the San Andreas occurred, once that boundary began, there's a little complicated story to all of that, but once that boundary began, it really began to relieve pressure on the North American plate. All right. For so long, that boundary was actually a convergent boundary. So if this is the North American plate and the Pacific plate was kind of crashing into it, kind of bunching it up. Well, that at some point movement changed, and it changed to a transform boundary. So now the San Andreas is kind of moving parallel, not really bunching up the North American plate. So the movement along the San Andreas is parallel to that boundary, and it allowed the North American plate to kind of relax. The North American plate wasn't getting butted up against, so it allowed the North American plate to start to relax and extend a little bit. Additionally, as the San Andreas is kind of moving along, it was actually also pulling on the North American plate as it's grinding up to, as the Pacific plate is now grinding to the northwest. It starts to pull on the North American plate a little bit. So because of the release in pressure from that convergent boundary changing to a transform boundary, and plus as the Pacific plate now moves along that transform boundary to kind of pull on the North American plate a little bit, it caused an extension. It caused North American plate to crack and extend, thinning out the plate, mantle material kind of pushing up more on this thinned out plate, further causing it to crack. Some stuff raised up, those are the ranges. Some stuff dropped down, those are the basins, basin and range. All right, and that's kind of like a satellite image. You can see this kind of uplifted ranges and kind of flat desert basins. So you see that in the terrain. That's kind of the long story short. So again, you have movement along the San Andreas Fault caused the North American plate to kind of relax, stretch, and thin out. Mantle material kind of pushed up on this now thinned out material, causing the crust to further fracture. Some material raised up, those are the ranges. Some material fell down, those are the basins. Now, here are a couple of videos and a geologic cross-section of Arizona that I want you to watch. So let's see, you know what, let me pause. Let me see if I can pull it up and maybe we can go over it real quick. Let me pause the video. All right, let me see if I can walk you through that link. Let's see if I can get it to play here. Okay, so this is an image of the Basin and Range province, what it looks like. You got these uplifted ranges, then flat basins, another range, flat basin. It extends through kind of a majority of the southwestern states. Again, when movement along the San Andreas occurred, it caused the North American plate to start to stretch and thin. Hot mantle material began to rise up as this plate was stretching and thinning, causing the crust to fracture. Some of the material got thrust up, and those are the ranges. Some of the material dropped down. That would be known as the basins. All right, so the mountains rise, the valleys drop. And so that's why we kind of see what we see around Phoenix. Flat area, basin, and then just these ranges of mountains popped up. All right, so looking at the width before and after, so the North American plate was extended by almost 30%, at least down in the southwest, at least that area of the Basin and Range province. Not all of North America was affected by this, just this area. So before and after, again, this area was extended by almost 30%. So thinning of the plate, mantle material creeping up, breaking the crust up, stuff went up, ranges, stuff went down, basins. But it's also this, as we get into ladder units and volcanisms and talking about Arizona, because the plate has thinned, it actually allowed an easier path for eventually molten material to kind of bubble its way up. Because the plate is thinned, and as material began to melt and bubble up, it allowed for volcanism in Arizona because of this whole scenario. because the plate's now thinner, because there's now cracks in it. Hot molten magma can now make its way up to the surface. Again, and all of this is due to mantle convection. So please check out that video. Additionally, let me pull up this. This is that second link that's on that page. So this is a very simplified look at a geologic map of Arizona. A geologic map looks at the surface geology, the kind of rocks that are at the surface, types of rocks and ages of rocks. This is a very simplified look at Arizona. It's actually much more complex. What I want to point out, though, is this line from southern Arizona up through Flagstaff. And this is along this line, we can look at something called a cross-section. A cross-section attempts to imagine slicing Arizona along that line and then tilting Arizona and looking at it from the side, almost like layers of a cake. What would we see kind of inside near the surface? So this is that cross-section from southern Arizona on through northern Arizona. So we can see in the southern parts of Arizona, we're in the Basin and Range province. We can see some material went up, some material went down, some material went up, some material that went down. And a lot of the material that went down is now covered by thousands of feet, sometimes miles of sediment. So that down-dropped basin, there can be, up to a mile deep of sediment covering it up. And as we get further up through the transition zone into the Colorado Plateau, you notice we don't have that uplifted material or down-dropped material. It's kind of one continuous kind of thing. There's no breaks. There's nothing going up. There's nothing going down. There's no faults, no movement. Just kind of a flat layer, but we do have volcanism as well as sedimentation in this northern part of Arizona in the Colorado Plateau. All right. Let me jump back to the PowerPoint. All right, welcome back once again. So again, the first link is that video that I went over. The second link is that map of Arizona. Please check both of these out. All right, this is not optional. These sorts of things may be on assessments. It may be asked of you to recall this knowledge, though. These aren't just, oh, hey, it's nice to go to these. No, please go to these. I'm telling you, watch them, go to them. These links can be found in the description as well. I've included these additional links in this lecture video down in the description. So that kind of brings us full circle in this tectonic cycle. So talking about seafloor spreading, ocean crust. So we're dipping around in here. All right, so we're going to spend the next couple of units talking about what's going on here. We'll talk about earthquakes, which are tied to plate tectonics. We'll talk about volcanism over here tied to plate tectonics. And then after we talk about that, now we're going to start to tiptoe into the rock cycle and what's going on there. That's going to be kind of our transition. But, in geology, kind of the three main cycles, as we talked about in Unit 1, tectonic cycle, that's usually where we begin. Now, I always get the question, well, okay, we know what the Earth looked like in the past, and we know plate tectonics is ongoing. What is the Earth going to look like in the future? Well, we just, again, follow the motions. 250 million years from now, this is what it will look like. So Pangea Proxima, so that's just a name. This is what it will approximately look like. You can see kind of how everything is rejumbled again. And we have a little separate Australia, Antarctica. So again, will be the next supercontinent 250 million years from now. All right. If you're around, check it out. That brings us to the end. So what are some of those big or main ideas as it pertains to plate tectonics? Plate tectonic theory, remember, highest level of knowing. Some of the past evidence, but also the current proof. We went over that in sections 1 and 2. Mantle convection, how it works. Similar to a lava lamp, so if you can use that as a model in your brain, that's how mantle convection works. The different types of boundaries, some examples, what they cause as far as, convergent, divergent, transform, examples of those, where are earthquakes and volcanoes more prevalent in regards to those type of boundaries. And then the basin and range formation, those 5 steps that I went over, and which has helped shape the vast majority of kind of central and southwestern Arizona. So that's it. That's all I got. Until next time, we'll see you then.